All right, Math 30-1, this is transformations lesson number 3. I'm going to go through it with you. We're going to do some of the investigations, but not all of them, of course. And then we will try to get through the class examples together. If you, at any point you need to pause the video, please let the sub know or set someone up to control the computer, and you guys can go as fast or as slow as you want through the lessons. So reflections part 1, lesson number 3. So moving on from translations, there is a definition at the top of the page. Underline, star, highlight that for yourself. You need to be able to recognize the term invariant points when it's used in a multiple choice question or numerical response or written anything. So an invariant point is a point on the graph which does not move after transformation. So we say it's invariant, varying meaning changing, so invariant, not changing. So comparing the graphs of y equals f of x as our original and y equals negative f of x. And so in part 1 it says, let's do a little bit of an investigation. This is the graph of x squared minus 10x plus 25. So an x squared graph, a quadratic type graph. Write an equation which represents y equals negative f of x. Well, negative f of x would be negative x squared minus 10x plus 25. And then I would have to distribute that negative, or on my calculator, I could just type it in. So y equals, let's clear this out, negative, and then in the brackets, x squared plus 10x plus 25 minus 10x. There we go. Okay, so we've got that in, correct? So x squared minus 10x plus 25 is the original. We're taking negative f of x, so I've put the negative in front of it. Let's graph it. And I can see it looks like the exact same graph. It was just flipped over top of the x-axis. Okay, says state the coordinates of any invariant points. Well, this x-intercept here at 5, 0 stayed the same. And so that would be considered an invariant point. It has one invariant point on the x-axis. In part 2, the graph of y equals f of x equals x cubed minus 8 is shown. So a cubic type graph, this little squiggly shape. Write the equation which represents y equals negative f of x. Okay, well, y equals negative x cubed minus 8. That would be acceptable. We should distribute that to show negative x cubed plus 8, so negative times the negative, and type that in. Use a graphing calculator to sketch and show on the grid. So negative x cubed plus 8. In my calculator, I graph that, and it seems to have been flipped across the x-axis. Looks something like that. That's a little bit off. Okay, going down and up that way. Okay, and so again, state the coordinates of the invariant point. Well, I had one invariant point right there on the x-axis. That is at 2, 0. Okay, you can see it better on the calculator that actually goes through 2, whereas my drawing is a little bit off. Okay, how does the graph of y equals negative f of x compared with y equals f of x? Well, I'm looking like, because this is symmetric, and in part 1 too, it's looking like it's getting reflected across the x-axis. Okay, and so in part 3, to compare, this is the graph of y equals f of x. Sketch the graph with y equals negative f of x, and developing or continuing with the pattern we have, I should be able to take this graph, flip it across the x-axis. So if I was 2 above the x-axis, now I'm 2 below. Anything on the x-axis stays the same, and then I should do a quick sketch. And so my graph would look like that. And then here's our note, our stop, take a look. Note, if you replace y with negative y, then y equals f of x becomes negative y equals f of x, which is equivalent to y equals negative f of x. So the replacement is an example of y equals, or y replaced with negative y. Now let's do a little quick proof of that, what they're saying. So they're saying, okay, let's start here at your original. Y equals f of x. Replace y with negative y. In other words, all of the y coordinates now become their negative partners, you could think of. So positives become negatives, negatives become positives, but the values themselves stay the same. So the values of y all get multiplied by -1. And we want to graph that transformation on f of x. And so instead of graphing, because we can't graph negative y equals, we graph positive y equals. So we're just going to do divide by -1 on both sides and get negative f of x equals y. So we've done the proof that if the replacement is y to negative y, the negative goes out front, kind of in front of the f of x, in front of the fancy way of saying y, and we see the translation across the x-axis. Or not the translation, the reflection across the x-axis. And so you're thinking, well, why are you saying y to negative y, and yet you're reflecting across the x-axis? Okay, wouldn't you think that would be the y-axis? Well, I want you to think y to negative y. This is how I think about it. Here's positive y, anywhere up here. Flip down to negative y. Y to negative y goes across the x-axis. So when we are going to talk, we're going to typically show, okay, we're at the top, the y-axis, or positive y to negative y, doing a flip across the x-axis. And so that's the only key thing you have to remember here. But as long as you know the replacement y and negative y, you can talk yourself through that. Okay. On the next page, comparing an original graph, so y equals f of x, to y equals f of negative x. The negative not outside in front of x, the negative actually on the x value in the brackets where the x would get plugged in. Take the graph y equals f of x equals x squared minus 10x plus 25. Write an equation which represents y equals f of negative x. Okay, noticing that this used to be x, and now it's replaced with negative x. So I got to go along, and everywhere I see an x, I got to replace it with negative x. So I've got negative x squared minus 10 times negative x plus 25. This one's a little bit harder to enter in your calculator using brackets, so we might as well just share it out. So we've got negative x all squared, so the squared goes to the negative and the x. Negative 1 squared is positive 1, so that stays as x squared. Negative, negative makes positive, so plus 10x plus 25. Okay, let's graph this one. The original graph's still on the page for us. Y equals, we've got x squared now plus 10x plus 25. Good. Graph it. And it's over here. And so I can see it's a parabola shape. The x-intercept is at -5. And so just do a quick sketch to show that it is now in a different quadrant. Use the graphing calculator to sketch. Okay, done. State the coordinates of the invariant points. Now, I really haven't drawn my graph high enough to see any invariant points, but this is headed towards the y-axis. This is headed towards the y-axis, and if I had continued this up, I could tell by the original equation that would pass through at positive 25, and so we can do a window on here to change our window to 30, and we should see it pass through at 25. If we want to verify that that is 25, we can go second, trace, go down to value. Number 1, it's going to say, what do you want x to be? I want to set x to 0 so I can see the y-intercept, and y is 25. And so the invariant point is at 0, 25, or that y-intercept at 25. The graph of x cubed minus 8 is shown again. Write the equation which represents f of negative x. And so that says take x, replace it with negative x. So again, y equals negative x now cubed minus 8. Now negative x cubed, or negative cubed is still -1, so that's still going to be negative x cubed minus 8. So no real change on the inside of the bracket. So bracket or without bracket, you can graph it. Let's plot it, see what happens. Negative x cubed
minus 8. Okay, here's the graph. I'm going to go back to the standard window. Okay, so I can see the squiggly thing is still down here, but it's flipped around from what it usually is. And it appears to be going like this. So it comes down, it does a quick curve, goes through -8, and then continues down. So I've done my sketch. State the coordinates of the invariant points being that one point right there that stayed on the same on both graphs. That is at 0, -8. How does the graph of f of -x compare with the graph of y equals f of x? Seems to be reflected across the y-axis. And building that pattern, take the graph of f of x in part 3, sketch the graph of y equals f of -x. I'm going to do a reflection across the y-axis, noting that this point should stay the same because it's on the y-axis. That would be invariant. One away from the y-axis, one away over here. 1, 2, 3 away over here. So I'm going to go on this side. 1, 2, 3. One away. Quick sketch. Okay, and so my graph has been reflected across the y-axis. It doesn't look too different because this graph is very symmetric, but we can see that the y-intercept stayed the same and the highest point, or the peak, the maximum, got shifted to the other side of the y-axis. And so on the bottom, this note, this guy's making all our conclusions for us. If we replace x with -x, then y equals f of x becomes y equals f of -x, and so the replacement is x to -x and results in a reflection on the y-axis. Okay, again, you might question, well, if we're saying the replacement is x to -x, why are we not saying a reflection on the x-axis? And so I like to draw kind of my grids to prove this, and like you'll see me, I'm usually throwing my hands all over the smartboard, but I like to say, okay, like let's imagine you were on the positive side of the x-axis. So there's the positive side of the x-axis. These are all positive numbers, right? This is the negative side of the x-axis. So if you flip from positive x to -x, you have flipped from x to -x across the y-axis. And so you're going to talk yourself through the x to -x, reflection across the y-axis. Okay, similarly, in that first investigation, when you talk about y to -y, you're going from the top of the y-axis to the bottom of the y-axis, and talking yourself through a reflection in the, or top of the y-axis to the bottom, and talking yourself through a reflection in the x-axis. Okay, last reflection we're going to do, comparing the graphs of y equals f of x and y equals f inverse x, or x equals fy. Surprise, surprise, we've seen this before. We've seen our inverse graph, we just were assessed on them. It is a type of transformation, so it falls under a reflection. And we've seen that before, but let's just do a quick proof. And so it says, if this is the graph of f of x equals x minus 5 squared, write an equation for which represents x equals f of y and solve for y. Okay, well, when we do that, inverse relations told us switch x and y. Now I'm going to have x equals y minus 5 squared, and then solve for y. So in this case, I'm going to have to square root. I'm going to take plus and minus. Square root x equals y minus 5, which means y equals plus or minus root x plus 5. Let's see if we can graph that. Now we're going to have to graph the positive root and the negative root separate. So I'm going to go root x, and outside my square root sign, I have to close the bracket. Plus 5, negative root x, close the bracket, plus 5. Okay, it gets graphed sideways. And starting at what looks like about positive 5 on the y-axis gets graphed like this. Okay, so what was once pointing up is now pointing to the right. use the graphing calculator to sketch. That we've done. Although there are 4 points of intersection, explain why there are only 2 invariant points and mark them on the grid. Okay, so 2 invariant points. So it's saying why would, since there's 4 intersections, 1, 2, 3, 4, why are only 2 of these classified as invariant points? And so we want to think about, I'm going to color 2 of them, this one and this one. Okay, and so when I was to focus on this one up here, I want to think about the coordinates. And so on the original, the coordinates look to be about 8,8, around there, 8,7. And when on my inverse, that is still 8,7. Okay, whereas here, or sorry, it should be 8,8. Yep, that's right, 8,8. That's still 8,8. Here looks at about 3,3. So that's at 3, 3, x and y. You're going to be switch them. It's still 3, 3. Now, it just so happens that these ones land as intersections because there was a pair that when you switched it, it became this, and then this one, when it got flipped, came here. So they did switch, but they didn't stay the same. And you can kind of prove that by doing it, like almost tracing it. And so if this point here is falling on the first part of the curve, then when we flip it, we don't want to say that that's still the same point, because in fact it moved up here. Okay, so I'll explain why there are only 2 invariant points. So although x and y coordinates switched and produced an intersection, only the only the 2 points actually remained the same. Okay, so you can almost argue the other 2 are a coincidence. Okay, so they did move. It just looks like an intersection, but an invariant point actually has to stay the entire time on the graph. Okay, which this one would have started at 3, 3. This one would have started at 3, 3. We would have switched it. It still would have been at 3, 3. So it's the same coordinate. It's not that it got switched from, what is this, around 7, 2, and going to 2, 7. That was a switch that resulted in a coincidental intersection, and not actually part of the reflection. Okay, in part 2, y equals x cubed minus 8 is shown. Write an equation for f inverse x. Notice some difference in notation. X equals f of y implies that this is not a function, which is true, because I'm looking across the x's. If I had done the vertical line test, 2 y values for every x value. Okay, so that they're using x equals f to y to show you they've switched x and y. They're implying an inverse function, or an inverse transformation almost, now we could argue, but it's not actually a function. Whereas here they're saying, hey, yep, that graph that you're going to get is going to be a function. It should pass the vertical line test. Okay, how do we deal with this one? We switch x and y first. So now x equals y cubed minus 8. We got to solve for y, so I'm going to add 8 and then take the cube root. Okay, I'm going to graph that. So I'm going to go down to math, cube root x plus 8. Okay, graph it. I see the squiggle now here at -8, and then passing kind of up. So I'm going to exaggerate that a little bit. There's the squiggle passing kind of slowly up that way. Okay, so again, which was once vertical is now becoming horizontal. Mark invariant points on the grid, one of them right there. How does the graph x equal f of y compare with the graph y equals f of x? This is the inverse, Whoops. And if we're talking about reflections, we say a reflection across y equals x, which we're going to call the mirror line. Okay. We have intended, or we look at part 3, we're intentional in trying to, again, flip this across based on the pattern we're building. We're seeing a flip across the line y equals x, which is the same thing we're going to do here. We treat it the exact same as inverses. So I'm going to switch my xy coordinates. So if I'm at -1, 2, now I'm going to be at 2, 1, or -1, 2, -1 down there. There we go. If I am at, like I'm seeing here, +1, 0, 0, +1. I'm thinking I messed up somewhere. Let's check this again. So -1, 2, that'd be 2. Oh yeah, this part's not on my graph. Okay, that makes sense. Okay, over here I've got -3, 0 becomes 0, -3. And I should have enough to draw a picture. Okay, so it's overlapping a little bit with my graph, but it should be starting here is the corner and then going up towards the top of the page and down towards the bottom of the page. If we replace x with y or y with x, then y equals f of x becomes x equals f of y, and this replacement is x to y or y to x, results in the inverse. This is for when it's a relation, that x equals f of y notation. F the -1x, we read that as f inverse x for when it is a function. Okay, so here's our summary page. So a reflection is a transformation which reflects or flips a figure about a line. Fill in the blanks which summarizes the previous investigation. So a reflection in the x-axis, if the graph is reflected in the x-axis, then it is the graph of, so I'm thinking x-axis, reflected in the x-axis, positive y to negative y, it is the graph of y equals negative f of x. And so the thin line here, the original, negative f of x, the transformed or the bold line. If the reflection, if y equals f of x is reflected in they're attending the y-axis here, if it's reflected in the y-axis, thinking y-axis, here's the y-axis, that takes me from positive x to negative x. So I'm going to do the replacement f of negative x, and that would take me from, positive. That would take me from this thin line here to the thick bold line, which is f of negative x. If the graph y equals f of x is reflected in the line y equals x, the mirror line, then is the graph of, and here's where we have the two notations, x equals f of y or y equals f inverse x, depending on whether or not it's a function. Okay, so y equals f inverse s or x equals f of y. And so here is the kind of our stop. If you wanted a summary, this is where you would come. Replacing x to negative x, you got a reflection in the y-axis shown by putting the negative x in f of x. If you're replacing y to negative y, you're reflecting in the x-axis shown by replacing y with negative y and dividing that -1 to be out in front. Interchanging x and y describes a reflection in the mirror line, and that mirror line produces that graph x equals f of y or y equals f inverse x. Okay, so I'm going to go through a couple examples with you, and I think we're going to leave our work on combining reflections to tomorrow. Okay, so the graph of y equals f of x is shown. Sketch each of the following graphs. So negative f of x, f of negative x, and x equals f of y. So using the definitions. Now here, this negative out front comes from y to negative y. That means positive y up top to negative y down below, y to negative y across the x-axis, which means take everything here, reflect it across the x-axis. I go right ahead and color in the 3 points on the x-axis to tell myself that they would be invariant, and the rest of them I take across the x-axis. So this one is 3 away, so I go 3 up, right there. Okay, from here, positive 6 will go to negative 6. And again. Until I have enough coordinates to draw the graph. And I've reflected it across the x-axis. Okay, so you only really have to take a few points. All of your y values are changing sign. That's the intention with the y to negative y. So I was taking the positive 6, making it negative 6, the negative 3, making it positive 3, and so on. Okay, in part B, y equals f of negative x. Noting the replacement they've done there, x replaced with negative x. Now that goes from positive x-axis to negative x-axis. That's across the y-axis. So the reflection across the y-axis, go ahead and color any points on the y-axis. There's 1. In this case, that is going to stay the same. And then take the rest of your points and reflect them across. So if this one is at 4, then now it'll be at negative 4. If this one is at negative 2, now it'll be at positive 2. At negative 4, it'll now be at positive 4. This one is at negative 5, it'll go to positive 5. And this one is at positive 7, we'll go to negative 7, but it stays in line. Okay, and do I have enough coordinates now to draw a picture? Oh, not quite. I need this one too. So this one's at 9, 0, negative 9, 0. There we go. So the graph gets reflected across the y-axis. You're taking your points, imagining there's a mirror along the y-axis and switching. Okay, the hardest ones to draw are the reflections across the mirror line. So x equals f of y, tricky because you have to imagine a line here that you're flipping over. Again, going through like 1, 1, 2, 2, 3, 3, etc., which means any invariant points lie on that line. So I could go ahead right there and color in 2, 2 because that's going to stay the same. But the rest of them, the coordinates have to switch. And typically it's very hard to visualize because your picture gets turned almost like a 90-degree turn, which it's really hard to picture. So if this is negative 5, 0, now becomes 0, negative 5. So 1 point at a time. Negative 4, 6 is going to become 6, negative 4. So find 6, negative 4. Negative 2, 6 is going to become 6, negative 2. 6, negative 2. Okay, 0, 4 is going to become 4, 0. This point stays on the graph. What other points do I have here? Down here is at 7, negative 3. Become negative 3, 7 up here. And then this point right here, 9, 0 will become 0, 9. Okay, so the best we can draw this. Up, across, down, it looks like, through here, and then here. So it's still kind of the same shape, it just got turned. Okay, a reflection off the mirror line, the hardest one to draw. Easiest way to do that is switch your x and y coordinates and then try to draw the picture from there. Okay, last class example. The graph drawn in the thick line is a reflection of the graph drawn in the thin line. So, okay, so the thin line's the original. Okay. Write an equation for each graph drawn in the thick line. So if the thin line is y equals f of x, and I end up down here, try to identify some invariant points, the points that are on both, that they stayed the same. This one down here, Then try to describe what line that ended up on. That ended up on the mirror line, y equals x. It's not on either the x-axis or the y-axis, and that will tell you what your reflection is. So this is a reflection in the mirror line, which means the equation of the graph drawn in the thick line is the inverse y equals -1, or f of -1, or f inverse x. This one right here, thin line becomes thick line, looking things over here, getting flipped over here, and invariant point on the y-axis. That means a y-axis invariant point, thinking what would flip over the y-axis from positive x to negative x. Make that replacement x to negative x in your equation. So f of negative x, which means last one we could predict is the third reflection we're going to see. And so we see here as our original, here is our transformed graph, an invariant point on the x-axis, things getting flipped from, oh, is this one, did I miss this one up? No, I don't think so. Maybe they're both. Oh no, this one's on the x-axis. Yeah, sorry. From positive y to negative y. It just looks the same. Okay, this one's from positive y, see it going down here, to negative y, keeping the x-axis the same. So that's going to be y to negative y. We're going to say y equals negative f of x. So if you look closely, you're going to see they're slightly different. This one is further out. So it is actually the reflection of this across and not this down. Okay, so just be careful. Look for your invariant points. Once you've identified which line to that you've reflected over, then you can go and write your equation. Okay, for your homework, complete assignment questions 1 to 6. So catching up all assignments from all questions on lessons 1 and 2 assignments, and then complete all of 1 to 6. And when we get back, we'll try some questions on combining reflections. All right, enjoy.